John Nash showed that every game has a Nash equilibrium. But as computer scientists, we should also ask the next question. Can we compute a Nash equilibrium for a given game? But this turns out to be quite tricky. The first problem we encounter is already that some games have the property that all the Nash equilibria of the game involve irrational numbers. And so no exact computation will be possible unless we use some non-standard output encoding at least. The solution is to lower our standards a bit and not ask for an exact solution, but only for an approximate solution. There are different ways in which we can define what an approximate solution would be, but here's the definition that we will use. We will say that a strategy profile, sigma star, is an epsilon Nash equilibrium if for all players I, and for all strategies of this player I, the payoff that the player gets when playing strategy sigma star I is at least as large as the payoff the player would get by playing a different strategy sigma I minus some epsilon. What this simply means is that no player can gain much by switching her strategy. She might be able to gain a little, but not more than epsilon in expectation. So every player is maybe not happy, but almost happy. She wouldn't be able to do much better by switching to a different strategy. Now, similarly, we should define what an approximate fixed point is. So remember the proof of Nash's theorem, we used Brouwer's fixed point theorem in this proof, and this will turn out to be useful also for the computation of approximate Nash equilibria. But for this we need the notion of an approximate fixed point as well. So we call a point x star an epsilon approximate fixed point of a function f if f of x star minus x star is less or equal than epsilon. And when I say is less or equal than epsilon, I mean x star and f of x star could be vectors or something like that. So we take the norm of the difference, and in this case I want to take the maximum norm. So we look at the maximum difference of any component of these two vectors. Intuitively, what this just means is that if we have this point x star, and we apply the function to it, it doesn't move much. So an exact fixed point would be x star doesn't move at all if we apply the function. An approximate fixed point is if we apply the function, the point doesn't move much. And now I will tell you a fact. And I will not prove this fact, I will just state this. And the fact is that every alpha approximate fixed point of the function constructed in the proof of Nash's theorem. Remember our previous video about the proof of Nash's theorem? Corresponds to an epsilon Nash equilibrium. And of course now I have to tell you what alpha is. And alpha in this case is epsilon divided by d squared times p squared max. And now, of course, I have to tell you what d and p max is. So let's say d is simply the sum over the sizes of all the pure strategy sets of all the players. So I just look at the total number of strategies in the game, like for all players together, and that is d. And p max is simply the ratio between the largest and the smallest possible payoff in the game. So the largest payoff that any player could get and the smallest payoff that any player could get, and you just take the ratio of the two. Okay, so now this gives us a path to compute an epsilon Nash equilibrium, because we can just construct the function from the proof of Nash's theorem and then find an alpha approximate fixed point in that function. And that will be an epsilon Nash equilibrium. Of course, now the question is, how do you find an alpha approximate fixed point in this function? Okay, so for this we need a theorem, and this is Scarf's theorem. What Scarf's theorem provides us is a way to use Sperner's lemma to find approximate fixed points of a function. Remember the proof of Brouwer's fixed point theorem from a previous video. Roughly speaking, we said that we can divide the domain of the function into increasingly smaller simplices. Every time, we can find at least one small fully colored simplex. And in the limit, the sequence of the fully colored simplices converges to a fixed point of the function. Now, we cannot use this to compute exact fixed points. And this is because this would essentially require us to create an infinite number of infinitely small simplices. But maybe we can use it to find approximate fixed points if we make the simplices small enough, but not infinitely small. So our hope is this: if we divide the domain of the function into simplices which are small enough, which have a small enough diameter, and then find one of those simplices that is fully colored, then maybe that will correspond to an alpha approximate fixed point. And Scarf's theorem formalizes exactly this idea. So let S be a d-dimensional simplex, which is subdivided into smaller subsimplices of diameter at most delta. Now, let f be some function from S to S, and this function should be continuous. Color every vertex of every subsimplex according to the rules that we've learned in the proof of Brouwer's fixed point theorem. And that means in particular that if a point V receives color I, then f of V is less or equal to Vi. And previously we talked about red, green, and blue. So here when I say color I just number the colors in some way. So maybe red is color 1, and blue is color 2, and green is color 3, and so on. Now, if delta is chosen such that it's at most alpha divided by 2d, and such that for all x and y from the domain of the function, such that x and y have a distance in the maximum norm of at most delta, then the images of the points x and y, so f of x and f of y, have a difference in the maximum norm of at most alpha divided by 2d. So delta is not too large, that's the first condition. And the second condition is just that if 2 points are sufficiently close together, then their images are also sufficiently close together. And you can read the exact constants here. So if the 2 points are close together, meaning have a distance of less than delta, then the images should have a distance of less than alpha divided by 2d. Okay, so if those conditions are met, then any point in a fully colored subsimplex is an alpha approximate fixed point of this function f. I will prove Scarf's theorem in a separate video. In this video, we'll just proceed and use this theorem. A slight warning here, I will be slightly imprecise and wave my hands at times. I will make slight technical inaccuracies in what I'm going to tell you. And this is because I think the technical details are not actually that interesting. I want you to get the big picture, the big ideas here. And so I will make some statements that are not fully accurate. If you like, you can try to find all the tiny mistakes I'm going to make and try to fix them. But hopefully you will just take away the main message from this video. So here's an important consequence of the theorem of Scarf. It's the following corollary, which states that there exists a constant C prime, such that if delta is less or equal to C prime times alpha divided by n times d cubed times p max, then any point in a fully colored subsimplex is an epsilon Nash equilibrium. So this basically just gives us a specific value for delta that delta should not exceed. And if this is true, so if delta is small enough, then in fact we get these Nash equilibria that we were looking for. And the proof of this corollary is not too difficult. It is enough to show that all these points in this fully colored subsimplex are alpha approximate fixed points of the function. One important fact we need about the function that is constructed in Nash's theorem is the realization that this function is sufficiently smooth. And what this specifically means is that this function in the proof of Nash's theorem is Cn d squared p max Lipschitz. And this just means that if you have 2 points, x and y, then the distance between the image points of those 2 points, so f of x and f of y, is no more the distance those 2 points, x and y, had times some factor, and the factor is exactly this c times n times d squared times p max. And c here is just some large enough constant. Okay, so this is a fact, and I'm not going to prove this fact. Just trust me that the function in the proof of Nash's theorem satisfies this particular Lipschitz condition. So it's a sufficiently smooth function. And if this is the case, then we can use the following reasoning. If the distance between x and y is less than delta, then the distance between the image points is of course less than c times n times d squared times p max times delta, because of the smoothness of the function. And now we just plug in the bound we have for delta in the statement of the corollary, which is c prime times alpha divided by n times d cubed times p max. And then we realize that a lot of stuff just cancels out, and we are left with just c times c prime times alpha divided by d, where this c and c prime are some constants. And we can now just pick c prime small enough, so smaller than 1 divided by 2c. And if we do this, we plug this in, we get that this whole expression is less or equal to alpha divided by 2d, which is exactly what we needed to apply Scarf's theorem and learn that indeed we found an alpha approximate fixed point. And so this now gives us a concrete number where we know what the diameter of the simplices has to be. So the diameter of the simplices has to be less than the c prime times alpha divided by n times d cubed times p max. To summarize, this is our algorithm to compute an epsilon Nash equilibrium. Find an alpha approximate fixed point of the function from the proof of Nash's theorem. And to do this, we just divide the domain of the function of Nash's theorem fine enough meaning delta has to be less or equal to c prime times alpha divided by n times d cubed times p max. And then we color all the vertices according to the rules in the proof of Brouwer's fixed point theorem, and we find a fully colored subsimplex. And then any point in that subsimplex will be approximate fixed point. The main remaining question that you should ask yourself as a computer scientist is, how long does this take? What's the running time of this procedure? And this largely depends on the number of subsimplices we need, because we need to find a fully colored one, and we don't have any good method of doing that rather than to just look through each one of them. So dividing a simplex that has dimension d and a side length of 1 into simplices of diameter delta can, of course, be done with O of 1 over delta to the power of d subsimplices. And this is basic geometry. Now, that means our running time is not more than in the order of n times d cubed times p max divided by alpha, and all of this to the power of d. And now, I mean, if we plug in the value for alpha that you can still find at the top right corner of the screen, then we have n times d to the power of 5 times p max cubed divided by epsilon, and all of this to the power of d. So our running time is somehow not more than in the order of this expression. The important part here is that this d is in the exponent. So the running time is polynomial in 1 over epsilon, which is nice, but it is exponential in d. And remember that d is the number of pure strategies in the game. So unless your game is very small, the running time of this particular procedure will be very large. So this is an algorithm to compute epsilon Nash equilibria. It works, but it's not particularly fast. So if you have anything but a very small game, this will take a long time. So is there something better we can do? We don't know exactly, but maybe not, and we will discuss this more in a later video.